In this session, we will be deriving the Jacobian of RRR manipulator or 3DOF manipulator. So we are going to use formula method for deriving the Jacobian. So the Jacobian matrix, it has n columns. So where n refers to the number of joints. So here in our case, we are going to now derive the Jacobian of 3DOF manipulator. So we have to derive J1, 3 columns, J2 and J3. Right. So each Jacobian, each column of the Jacobian, it have linear Jacobian component and angular Jacobian components. So the formula to derive the linear Jacobian component is different if it is depending on whether the joint is revolute or prismatic. So if it is revolute, we have the linear Jacobian component, we will be using the cross product of Zi minus 1 into On minus Oi minus 1. And if it is a prismatic joint, the linear Jacobian component is Zi minus 1. And for angular Jacobian component, for revolute joints, it is Zi minus 1, and for prismatic joint, it is 0. So we are deriving the Jacobian for 3R manipulator. So the figure of a 3 of manipulator is shown in figure. So with the 3 links with length L1, L2 and L3 each, and it has 3 joint angles theta 1, theta 2 and theta 3. Right. So we have the transformation matrix that we have already derived in the earlier session for while we derived the kinematic model for RRR manipulator. So we'll directly use that. So T1 to 0, T2 to 1 and T3 to 0. But for deriving the Jacobian matrix, we need all the transformation matrices related to the base time. So we have to get T2 to 0. We have T2 to 1, but we have to get T2 to 0. How will we get it? So we'll be multiplying the transformation matrices T1 to 0 and T2 to 1. So multiplying these two matrices will be getting T2 to 0, right? So now once we have got those transformation matrices, the positional vector component. So this is nothing but O1 and this is your Z1, right? The same way here for T3 to 0. So this part, this is your O3, that is O3 relative to 0 frame, and this is your Z3, right? This is your Z3 to 0, right? Similarly, from the transformation matrix T2 to 0, you need to get the Z2 and O2 value. So here I have just multiplied and I have got the transformation matrix T2 to 0. So in that, so this is your Z2 and this is your O2. Right. So as I told earlier, we have to get 3 columns of the Jacobian matrix. So first we'll get J1. So all the 3 columns are related to revolute joints. So we'll be using the linear and the angular Jacobian formula for revolute joint. So it is the first linear velocity component. It is Z, cross product of Z0 and O3 minus O0. So just multiplying or the taking the cross product of the two vectors. So Z0 vector and O3 minus O0. So this is O3 minus O0 vector. So how will you get it? So first hide the first row and multiply these two elements, right? And so 0 into this minus 1 into this. So the first element you will be getting as minus S1 into L3C23 plus L2C2, right? And in the same way, the second element, how we'll get it? So you have to hide the second row. So you have to hide this second row. So 0 into this element minus 1 into this. So already for second row you have a minus. So that minus of minus will get cancelled and you will be getting C1 L3C23 plus L2C2, right? And for the third row, it is simply 0. You have to hide this last row. So you'll be getting 0 into 0, 0 into 0. So it will be simply 0. and Zi minus 1, that is here it is Z 0, it is 0, 0, 1. So just you will be getting 0, 0, 1. So this will be your J1 column, right? This is your J1 column. So that is what I have just written here. J1 is equal to this column, that is minus S1 L3 C23 plus L2 C2, C1 L3 C23 plus L2 C2, and 0, 0, 0, 1. The same way you have to also get J2. Now the formula is Z1 uh, and O3 minus O1, cross product of Z1 and O3 minus O1 and Z1 here. The angular Jacobian is Z1, right? So you have to get the cross product of these two vectors. The same way how I just explained for J1, you have to get the cross product of these two vectors, and then which combining we will be getting the J2 column. So this is the J2 column, and the J3 column also you have to get it in the same way. So Z2, cross product of Z2 and O3 minus O2. So this vector is O3 minus O2. So the cross product will be the hiding the first row. So minus C1 times L3S23 minus 0 times this. So that will simply minus L3S23 C1. Okay, that is the first element. And for the second element, to get the second element, you need to hide the second row. So you will be multiplying S1 times L3 S23, right, minus 0 into this. So already you have a minus for that second element. So that is why you get a minus here. So minus L3 S23 S1. And to get the third element, so it is you have to hide the last row. So it is simply multiplying. So what you get? So you will be getting S1 squared L3 C23 minus C1 into this. So minus of minus plus. So plus C1 squared L3 C23. So taking L3 C23 common outside, you will be getting S1 squared plus C1 squared. So that is equal to 1. So simply the answer will be L3 C23. That is why the third element here it is L3 C23. And then followed by that the angular Jacobian component, it is simply Z2. So S1 minus C1 0. So this is J3. Now combining all the three columns J1, J2 and J3, you will be getting the Jacobian of the RRR manipulator.